are live.
Yeah, okay. Share the screen, please.
Just a second. Yeah.
Yeah, so it's a pleasure for me to invite you all to enjoy learning physics with conceptual and problem-based approach in this evening, organized by National Academy of Sciences, India, Nasi, Delhi chapter. And we have with us the second speaker today, Dr. Vaibhav S. Prabhudesai, from the Department of Nuclear and Atomic Physics, Tata Institute of Fundamental Research, TIFR, Mumbai. Dr. Vaibhav did his master's in 2000 from IIT Mumbai, where he had won the Best Project Award. He received his PhD in 2006 from the Tata Institute of Fundamental Research. His PhD thesis title was Free and Rydberg Electron Attachment to Molecules. He completed his postdoctoral fellow in 2007 from TFR itself and another one from Weizmann Institute of Science, Israel in the year 2010. He is the recipient of INSA Medal for Young Scientists in 2008, SN Ghosh Award for Young Scientists in 2006, Geeta Udkaukar Award for Best Thesis in 2006, and Indian Physics Association, IPA, Young Physicist Colloquium First Prize in 2005. He has a research experience of more than 14 years, and he has published several research papers in national and international journals. Welcome, Vaibhav, and I hope you don't mind calling me directly with your name. So you're welcome, and we are really grateful that you agreed and spared out some time to interact with our students regarding molecular physics, which is your forte, and please share your screen and deliver your talk. Me, along with the organizing committee, is really grateful, or we are really grateful that you could take out time for interacting with our students. Dr. Vaibhav will also be there with us tomorrow evening in the first session. So students, please enjoy. So did you choose, do you want to show a Chrome tab or a window? A window.
No, I will show
Chrome.
Window.
So you have to open that window first.
Okay, you want, okay, just a minute.
So your window which you want to share should be opened first.
Yeah, there was something else which was getting shared. Okay.
It's no problem. Yeah.
Okay. So,
yes, perfect. Born Oppenheimer approximation. Thank you so much. Please go on.
Yeah. So thank you, Dr. Punita, for giving me this nice opportunity to interact with all the young students and maybe discuss with them some of the ideas that people have used to understand how molecules behave and what are the properties that they show and how we can learn those properties by doing spectroscopy. And particularly I will be interacting with you all, discussing about some of the aspects of molecular spectroscopy, namely the vibrational and rotational spectroscopy. And if time permits, I will also discuss a little bit about Frank-Condon principle and maybe Raman spectroscopy. Now, I personally enjoy any such session if the session is interactive. And that is why what I'm going to do is once in a while, I will be asking questions and I expect people to, without raising hand, if they know the answer, they should just spell out, they should just speak and tell me the answer, because that way I make sure that people are paying attention and they are also, around and not leaving the screens. So Professor Bapat has already explained to you that how a simple molecular system like H2 plus and H2 can be understood in terms of Hamiltonian, of electron and nuclear part of the molecule. And also he has explained to you how one can attempt to solve this Hamiltonian and obtain energy levels and wave functions for different states, including the ground state and the excited state, etc. And he has also explained to you what is the most crucial approximation, because this is a very, very difficult problem to solve. if one do not incorporate some of the crucial approximations, and one of those approximations is the Born-Oppenheimer approximation. And this is the approximation in which we assume that the electronic motion is so fast compared to the nuclear motion that we can in principle separate the two. We can treat the coordinate of the nuclear entities in the molecule as parameters for the electron motion. And the whole idea is that use this parameterized part of the equation and use it to actually determine the potential energy and the wave function for the electronic part of the system. And now, once you obtain this potential, use this potential to understand how the nuclei and the nuclei are behaving, and what kind of motion and what kind of energy states that they show up. So just quickly go through quickly on Born-Oppenheimer approximation. The main feature of the Born-Oppenheimer approximation tells us that the 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 Hamiltonian has eigenvalues and a corresponding eigenfunction, which are the molecular wave function. And these wave functions actually have two parts. And these two parts will comprise of electronic part, which Professor Bapat has explained to you how to find them. And then they will have a nuclear part, which will comprise of which will depend solely on the nuclear coordinates. And when you solve the electronic part of the wave function and obtain the potential energies of the system, this potential energy is the one which actually is used by or is the potential energy or potential under which the nuclear part of the wave function is actually going to perform its motion. Now, you must have seen, Professor Bapat must have shown you how the electronic potential energy curve looks like for a typical diatomic molecule, particularly for H2 and H2 plus. And if one goes for that and completely neglect now the electronic motion and just stick to the nuclear motion, then as any Hamiltonian is, it has two parts. One is a kinetic energy part and the other is a potential energy part. And as I said earlier, the potential energy part comes from the electronic potential that electron provides, and that's basically gives you the bonding and anti-bonding features of the wave function. And if the nature of the electronic part of the wave function is a bonding type, then you will have a potential energy curve which will have a minimum. And that's what happens for H2 plus and H2 ground state. And that's what Professor Bapat has explained very nicely. So let's assume that right now we have obtained these electronic potential energy curve. So now, if we consider only nuclear motion, then because in diatom there are two nuclei, the kinetic energy term will comprise of two parts, and each of them will correspond to each of the nuclei. And now, because these two nuclei are moving in the presence of the potential energy, which has come from the electronic motion of the molecule, you can actually rearrange these terms and show that this overall nuclear motion can actually be broken down into motion of a reduced mass. So a single particle motion which has a mass which is equal to the reduced mass defined as m1 into m2 upon m1 plus m2. And then correspondingly, there is a reduced momentum. And then the total mass and the total momentum, which will behave like a center of mass motion. Now, the center of mass motion we can completely take out, because that is something which is which the molecule will show in a free space, and that is not something which will determine the internal structure of the molecule. That will deal with the entire molecule as a single particle, which is moving with the mass as a total mass of the molecule, and that will follow all the thermodynamics and kinematical equations that you get from thermodynamics and kinetic theory of gases. So when we say that a molecule behaves like a point mass, it is this capital P square by 2m term which actually comes into picture, and that's where the center of mass motion, and hence the molecular motion as a point mass, is assumed in the kinetic theory of gases. So we are not going to worry about that part. What we are going to worry about, or what we are going to take into account, is the internal structure and the internal motion that this nuclei show. And when I say internal, it is not inside the nucleus, it is the internal to the molecule. Okay. And that corresponds to this P, small p square upon 2 mu term of the kinetic energy in the Hamiltonian. Now, can somebody quickly tell me, if I have a homonuclear diatomic molecule, say H2, what will be typical value of this mu? Anybody? You can tell me in terms of atomic unit or atomic mass units, and that's fine.
So students are writing m by 2.
Writing m by 2.
Yeah.
Very good. So as you can see, that when you talked about a reduced mass in the electronic spectrum, that reduced mass was entirely of the mass very close to the mass of electron. In fact, in the atomic spectrum, you must have seen that the discrete atomic levels get slightly shifted, because the mass of electron is not the rest mass of electron, but it is a reduced mass of electron, as the nucleus does not have infinite mass, it has a finite mass. And that's why with the bound system of electron and nucleus actually alters the mass of electron. Exactly in the same way, this particular system has two nuclei, and because the mass of two nuclei are comparable, the reduced mass of the system, which will behave like a single particle now, will have mass which is comparable with the mass of the nuclei. And now this is very important, because this is where now the typical energy scales will come into picture. So as you must have seen that Professor Bapat have shown you the potential energy curve, which actually deals with or tells you about the typical energy scale at which the electronic motion takes place. And that electronic motion and that energy scale is few electron volts. And I hope you all know what is electron volt. An electron volt is an energy scale, which is basically nothing but the energy gained by electron when it passes through a potential difference of 1 volt. And in joules, it is of the order of 1.6 into 10 power minus 19 joule. So typical energy scales or energy levels for electronic energies of molecule, they lie in their energy scales of few EVs. So obviously now, and you must have also seen in the atomic physics class that the typical kinetic energy, for example, in the atomic in the hydrogen atom, the typical kinetic energy of electron is of the order of few eV. So if that is the case, then in the similar fashion, what will be the kinetic energy, or what will be the energy scale for the nuclear motion? Now this has two-pronged answer. The one part of the answer would comprise of what kind of motion that we are looking into. So there are two types of motion, and that's why there will be two types of answers. So as far as the diatomic molecule is concerned, there are two types of motion that can formulate the internal motion of the system. The first type of motion is something called vibration, where the two molecules or two nuclei are talking to each other, and they are bound by some bond, and this bond has some flexibility, and this flexibility imparts a vibrational motion to the molecule. And the second kind of motion is going to be a rotational motion, because now your molecule will look like a dumbbell, and a dumbbell in a 3 dimension can in principle rotate, and that will be another kind of motion that the molecule will show. Now, typically, the rotational motion of molecule is like a circular motion, and the corresponding mass that is rotating in molecule is a reduced mass of molecule. Now, do you know what is a typical ratio of mass of electron to mass of nucleus? Is nucleus heavier than electron, or electrons are heavier than nucleus?
The nucleus is heavier, students
Nucleus
right?
heavier. Yeah.
Very good. And by what factor?
1896 times the proton.
Of the order of 2000. So
Yeah.
obviously, if nuclei are heavier than electrons, the kinetic energy corresponding to nuclei are going to be about 2000 times smaller, or about 1000 times smaller than kinetic energy of electron. Because if you remember, typically the momenta are same, p square by 2m, and because the mass coming in the denominator is 1000 times larger for nuclei, the corresponding kinetic energy for the same or similar amount of linear momentum would be 1000 times smaller. Now, where does this momentum come into picture? This comes into picture for rotational motion. So obviously, the energies associated with rotational motion will be typically 1000 times smaller than what is the energy levels or energy scales corresponding to electronic motion. So what is this electronic motion scale? As I said, it is of the order of electron volt. So obviously, the corresponding rotational motion will have energy scale of the order of milli electron volt or smaller. Now, when I talk about milli electron volt, what kind of spectroscopy that comes to your mind? Or when I talk about electron volt, what kind of spectroscopy does come to your mind? Or in other words, if I say that a transition takes place in a molecule from one energy level to another energy level, the typical energy difference between the two states is going to be of the order of a couple of electron volts. So if that is the case, and if such a transition is going to give out a photon, what kind of wavelength or what kind of frequency do I expect these photons to show?
So Sejal has replied visible light.
Exactly. So for electronic transition, that means the typical spectroscopy will be in visible and ultraviolet range. So now, if few EVs corresponds to visible and ultraviolet, what would be the energy scale, or what would be the frequencies or wavelength scale for few milli EV or several micro EVs? Any idea?
They have written 10 to the power 14.
14 or 15.
What? 10 to the power 14 or 10 to the power 15 what?
Write the unit, Sejal. Hertz.
Yeah. So how much does that transform into in the form in terms of wavelength, and what kind of waves are those?
500 nanometer.
500 nanometer.
Yeah.
Now, so this is where now we have to understand that a 500 nanometer is typically a visible light. And we have already seen, and you have correctly answered earlier, that the electronic transitions are going to show me visible light. So if 500 nanometer, which is going to be a visible light, is going to be my electronic transition, what would be my rotational transition if their energy scales are 1000 times smaller? Yes, what is the answer?
Infrared.
Infrared and microwave as well.
No. So now you have to, now you are spanning a quite a long length range, you see, from microwave to infrared. So that's not fair. So let's stick to one. So if I mean, it's very simple estimate, and this is what first thing that as a student of physics you should learn how to imagine and do a back of the envelope things. So as I said, 500 nanometer is a visible light, and if my rotational spectrum going to be 1000 times lower in energy, that means my wavelength is going to be 1000 times longer. So what is 1000 times longer than of 500 nanometer? Yes. What are
Good
the?
quiz you are taking.
I'm sorry.
I'm saying good quiz that you are taking.
Yeah.
Microwave, some are writing X-ray. Even
X-ray.
I'm
even
asking a
YouTube
very simple
comments are
question.
full.
No,
Yeah.
I'm asking a very simple question. You have a 500 nanometer light, which corresponds to energy of few EVs. And now I'm saying that my energy is reduced by factor of 1000. What should happen to my wavelength? Should my wavelength increase or should my wavelength decrease? First, answer me that.
Decrease.
Decrease.
No, wavelength should increase because longer wavelength should have a lower energy, shorter wavelength should have larger energy. Do you agree with this?
Chetna, Sri Lakshmi, many are writing increase. Yeah.
Yes, exactly. Now, if the energy decreases by factor of 1000, then the wavelength should increase by factor of,
1000 times.
correct? So now, if my wavelength of few EV corresponds to 500 nanometer, what should be the wavelength if my energy is reduced by factor of 1000?
500 micron. Some has written. Jahang has replied 500 micron.
And that is the correct answer. It will be of the order of a few hundreds of angstrom. So now, can you tell me what part of the electromagnetic spectrum that has half a millimeter wavelength? 500 micron is half a millimeter. You agree? So what part of the electromagnetic spectrum has half a millimeter wavelength? Yes? What are they saying?
Microwaves.
Fantastic. It is microwave. And that's where most of the confusion comes, is that when people say microwave, people think it is 1 micron. Microwave is not 1 micron. Microwaves are of the order of 1 millimeter. Now, do you know where have you used this microwave?
Communication ovens.
Ovens. Ovens is more important than communication.
Radar systems.
We have used microwave in ovens. And do you know what is the principle of microwave heating the food? Yes.
Many different answer. Vibration of molecule, rotational energy resonance, vibrate the molecules of food, rotation energy, dipole moment.
We just now have seen that rotation of molecule is 1,000 times weaker in energy than electronic motion. And rotation of molecule is something which happens to be in a microwave regime. So if I'm shining a microwave on some substance, and if the substance is absorbing that light, then it definitely is a rotational spectrum which is coming into picture. So then what about vibrations? So now I tell you something interesting. Professor Bapat has shown you that potential energy curve that you guys have derived for the electronic motion, or from the electronic motion. And in that potential, your molecule or your nuclei are going to move. So if the two nuclei are going to get bound by this electrons sharing between the two nuclei, then this entire system will behave like a spring. And if you have a spring, you have a spring constant. And if you have a spring constant, you also have something called the fundamental frequency. Now, what is the fundamental frequency of vibration of a mass attached to a spring? If mass is m and spring constant is k, what is the frequency omega? It is square root of k by m. Now you imagine the mass is of the order of 1,000 times than the mass of electron. So the energy scale will be square root of 1,000 times smaller than the energy scale for electrons. So what was the energy scale for electron? Few EVs. So what is going to be the energy scale for vibrations? Square root of 1,000 times smaller. Now typically square root of 1,000 is of the order of 30. So you can say that if Q EVs is my energy of photon for electronic transition, then the energy scale for vibrational transition are going to be of the order of 30 times smaller. Now 30 times smaller of 500 nanometer would be 30 times smaller energy correspond to longer wavelength or a shorter wavelength than 500 nanometer?
Some are writing shorter, other are writing longer.
No.
Longer, many are writing
Yeah.
longer. Yeah.
It has to be longer because energy is going down. See, energy and wavelength has an inverse proportionality. Longer the wavelength, lower the energy. So now, since the energy is dropping by factor of 30, the wavelength is going to go up by factor of 30. Now, what is 30 times 500 nanometer? About 15 micron. Okay, so that's a little bit on higher side. So we can say, okay, of the order of 10 micron. What is that spectrum? Which part of the electromagnetic spectrum is 10 micron wavelength?
Infrared, sir, they are replying.
That's correct. And that's what I have written on my slide, because you can say, see that from 1 micron to 100 micron is the energy scale or is a wavelength scale that corresponds to IR, infrared. And that is where the vibrational spectrum comes into picture. So the first thing that we have made clear to ourselves is that the energy structure or energy levels of the internal structure of molecule which correspond to nuclear motion, there are two types of energy scales. One corresponds to the rotational motion of molecule, the other corresponds to vibrational motion of molecule. The spectra or the spectrum that is going to come out of rotational motion of molecule is going to be a microwave spectrum, and the spectrum that is going to come out of vibrational motion of molecule is going to be infrared spectrum. Good. So once we are clear with this, let's look into little more details about rotational and vibrational spectrum. Now, before going to vibrational spectrum, I actually would like to spend a little bit time on pure rotational spectrum because that has more classical analog and that makes, in understanding much clearer. So let's look at rotational spectrum of molecule. Now, the first thing that comes into picture for any rotation is something called moment of inertia. Now, for a diatomic molecule, it's actually a dumbbell shaped molecule. And since it's a dumbbell shaped molecule, as you can see HCl, it typically has three axes of or three components of moment of inertia that corresponds to three axes. Now, out of these two axes, the moment of inertia are going to be same. Can you tell me what are those two axes for which the moment of inertia of this diatomic molecule going to be same? It's written on the screen, but can you tell me what is this B axis and C axis would be?
Perpendicular ones to the line joining Y and Z.
Exactly. So suppose if you have molecule like HCl, hydrogen chloride, then the bond of hydrogen and chlorine, suppose if you consider that bond to be along the Z axis, then the X and Y axis are going to be the two axes about which the moment of inertia are going to be equal. Now, the first approximation that one can do for linear molecule is that you can consider the third axis moment of inertia, which is along the bond axis, as 0. And if you do this, then what we have is a rotator. If we assume that the third axis, which is the bond axis, the moment of inertia is not 0, then we have two types of tops. One is a prolate symmetric top, where the third axis a moment of inertia is smaller than the equal moment of inertia of this other two axes. And a nice example is CH3F, which is fluoromethane. And if the third axis moment of inertia is larger than the other two axes equal moment of inertia, then it is called oblate symmetric top. And a nice example of that is boron trichloride. Okay, so these are polyatomic molecules, and on those polyatomic molecules, we have this symmetric top kind of a system. But for a diatomic molecule, which we will be concerned today about, we can consider easily that the third axis of moment of inertia along third axis, the moment of inertia is 0, and we will be bothered only about the other two axes which are perpendicular to the bond of the molecule. And then there is another type of molecule which is spherical top, where all three axis moment of inertia are equal, and they are the most symmetric molecules, like methane, where you can go by all three axes and you end up with the same moment of inertia. And the most common, you will be surprised, but most common case is the asymmetric top, where all three axes are different. The moment of inertia are different. Good. So let's consider a rigid rotator, and let me do a very simple classical mechanics, which you guys must have done in 12th standard or 11th standard, but let me just revise it for you. So for rigid rotator, let's define something called center of mass. And when I define this center of mass, so there are two masses, mass m1 and mass m2. Now m1 and m2 are the two nuclei. And if they are separated by a distance r0, which is the bond length, then the center of mass is at point C. And suppose if it is at distance r1 from mass m1 and r2 from mass m2, then the moment of inertia for such a system for this center of mass can be written as m1 r1 square plus m2 r2 square. And then by definition of center of mass, which tells us that m1 r1 should be equal to m2 r2, we can say that the overall center of moment of inertia can be written down for such a system as mu r0 square. And the calculations are right in front of you. And you must have done this in your 11th and 12th. So now with this reduced mass and with this moment of inertia, let's look at the rotational spectrum. Now the rotational spectrum, and we will come back to this rotational spectrum, why it looks like this. We will come back to this when we will look at the quantum mechanical picture for molecule. But for the time being, just take it from me that the typical energy spectrum for rotations, they look like Ej, which is equal to h square upon 8 pi square times moment of inertia I multiplied by j into j plus 1, where j is called the rotational quantum number. Just take it from me, okay? And now this is in joules. This expression is in joules. And typically in spectroscopy, people prefer centimeter inverse or wave number as the unit. And for that unit, you have to just divide this expression by hc, where c is the speed of light. And if you do that, you happen to get h upon 8 pi square c into I times j into j plus 1. And this h upon 8 pi square c times I is an entity which is also called B, which is called rotational constant of a molecule. So obviously, by looking at this, I can see that the rotational levels will look like for j equal to 0. So j is a rotational quantum number. And this quantum number takes value 0, 1, 2, 3, 4. The corresponding energies are going to be j equal to 0 will correspond to 0 energy, j equal to 1 will correspond to 2b, j equal to 2 will correspond to 6b, j equal to 3 will correspond to 12b, and so on and so forth. So now if there is a transition that takes place from j equal to 0 to j equal to 1, which is absorption, the energy of the photon which is absorbed will be 2b. If the absorption takes place from j equal to 1 to j equal to 2, then the energy of the photon which is absorbed will be 4b. If the absorption takes place from j equal to 2 to j equal to 3, then the energy of photon should be 6b, and so on and so forth. So in general, if I have a rotational transition happening from j to j plus 1, then I have typical energy of 2b times j plus 1 in centimeter inverse. And the corresponding selection rule, as you can see, is delta j equal to plus minus 1. Now this is pure rotational. This is pure rotational spectrum. And as you can see that the rotational lines are located at energy 2b, 4b, 6b, 8b, and so on and so forth. So that means the distance between two lines, or the difference between two lines, will be 2b. So as you can see from this, in a pure rotational spectrum of a rigid rotator, you expect the rotational spectral lines to be shifted by a fixed amount 2b. Now, this brings us to the first type of questions which are typically asked. And that is, if I know the frequency or if I know the wave number of a specific transition of a diatomic molecule, say in this case, for carbon monoxide molecule, if the wave number for transition from 0 to 1 is 3.84, and now it can be measured very accurately, so 3.84235 centimeter inverse, can you determine the bond length of carbon monoxide from this? And yes, we can determine bond length, because once you know this transition, we know that a transition from 0 to 1 for a pure rotational spectrum has the energy of 2b. So therefore, the 2b is equal to this wave number, tells me that the b has a value of 1.92118 centimeter inverse, which gives me the moment of inertia, because we know that b, which is a rotational constant, is h upon 8 pi square c into I in centimeter inverse. So if I now reverse this equation, I get moment of inertia as something 14.5695 into 10 power minus 47 kilogram meter square. Now for carbon monoxide, the reduced mass is mass of carbon multiplied by mass of oxygen divided by mass of carbon plus mass of oxygen. And that tells me that the reduced mass of this system is of the order of 11.4 into 10 power minus 27 kilogram. Now, if I know the reduced mass and if I know the moment of inertia, I can estimate R square for a dumbbell. And from that R square, I can determine the equilibrium bond length of carbon monoxide, which happens to be 1.131 angstrom. Okay. And these are the mass of proton, and correspondingly mass of carbon and mass of oxygen has been taken. So this is a typical kind of a question that usually is asked about from the rotational spectrum, pure rotational spectrum. Can one determine the bond length of a molecule? Now this has a very, very interesting further effects, and we will come to that little later. But is this clear to all? How I calculated the equilibrium bond length by looking at the pure rotational spectrum of a molecule? Is this clear? Yes?
Yes, sir. Yes.
Good. Very good. So let's go ahead and look at this rotational spectrum little more carefully. And that will tell us or bring us to the next type of question that typically asked on rotational spectrum. So for a given rotational energy, Ej, which is nothing but h square upon 4 pi square, 1 upon 2i times j into j plus 1. And if I divide this by hc, I can say it is b into j plus 1. Now for this rotational energy, I can also write this rotational energy as half I omega square. If you remember your simple classical mechanics from 11th and 12th standard, I can write this energy as moment of half moment of multiplied by moment of inertia multiplied by omega square, where omega is my rotational frequency. And the corresponding angular momentum is I times omega, where I is the moment of inertia and omega is the angular frequency. And hence, just on similar to the, or in analogy with the linear or translational motion, I can write down energy as p square upon 2i. And if I write that, then the momentum, the angular momentum will take a form for rotational motion. It will take a form square root of j into j plus 1 multiplied by h cross, where h cross is Planck's constant h upon 2 pi. Now, for a given j state, there are 2j plus 1 degeneracy. And what is this degeneracy all about? So this is again a part of quantum mechanics. And that degeneracy is following. If you have certain axis, and with respect to, say, in this case, z axis, if your moment of inertia, if your angular momentum has certain values, so in this case, for example, if I have j equal to 1 state, then for j equal to 1 state corresponds to the angular momentum of square root of 2h cross. For that angular momentum, if I draw a vector, because angular momentum is a vector, if I draw a vector of that length, this vector, the quantum mechanics tells us, cannot just orient in any direction. Its orientation also has a quantized direction, and the quantization happens in a specific z-axis such that the component of this angular momentum along the z-axis has to have an integer value. Now this brings in additional quantization of this angular momentum. So in this case, for example, when I have j equal to 1, I have the value of angular momentum as square root of 2h cross. And this square root of 2h cross can have three components or three values of component along z-axis. One is obviously 0, but the other can be plus h cross and minus h cross. That means it can go in the forward direction or in the backward direction as compared to the, or with respect to the z-axis. So there are in principle three orientations of j or pj which are allowed for this state. However, if you look at the energy and if you look at the Hamiltonian, and we will come to the Hamiltonian little later, the Hamiltonian does not depend on the orientation of the momentum. What does it mean? It means that all three orientations of this angular momentum will have same energy, because Hamiltonian does not distinguish between the three orientations. So energy won't be distinguished for these three orientation. That means energy going to be the same. And if several states have same energy, then they comprise something called degeneracy of that energy level. So obviously, in this case, the J equal to 1 state of rotational level will have the degeneracy of 3, which is 2J plus 1. So every angular or every rotational level J will have a multiplicity or degeneracy of 2J plus 1. Now this brings us to the next question or next type of questions which are typically asked. And that is, at a room temperature or a temperature T, Kelvin, typically how much is a population of J rotational level as compared to the ground state of rotational level? And the answer to that is the population distribution in different rotational levels will go by the partition function, and the weightage of the rotational level J, or the number density of rotational level J, will be exponential minus Ej, where Ej is the energy level of that rotational level, divided by kT. But this is true if this happens for just one level, but each level has a degeneracy of 2J plus 1. Hence, we have to multiply this factor by 2J plus 1. So if you include now the degeneracy, I can say that Nj, or the number of particles in J state, will be proportional to 2J plus 1 times exponential minus energy of that level, which is BHC into J plus 1 divided by kT. And now if I differentiate this with respect to J to find out where does this population becomes maximum, I can differentiate this Nj with respect to J and equate it to 0. And the corresponding value of J that I will get will be the value for which I have the maximum population that will be present in the rotational energy levels. Any question?
Student, please write in the chat box or on the YouTube comment box for any questions.
Okay, if there are no questions, then I will just quickly.
Yeah, no questions. Yeah.
Yeah, so I will quickly go ahead. So by this, I can know that the maximum population will not be at J equal to 0, because that's what you expect, isn't it? One expects that the maximum population would be at the minimum energy, which is at J equal to 0, but that's not what happens at finite temperature. At finite temperature, because of degeneracies of higher J states, the maximum J, or the J for which the maximum population is present, corresponds to square root of kT upon 2BHC minus half.
So one small question is there from Dinesh, that what we mean by J max to be 0.
So it is not J max which is 0, it is a derivative of Nj with respect to J is 0. And when do you equate derivative to 0? When do we equate derivative to 0?
For extremum.
Exactly. So we are getting extremum by this, and I'm calling it maximum, but this is an exercise that you can find out that if I take that second derivative, then at this value, the second derivative would be negative. This tells me,
One small question from Ritu sir, that EJ would be energy difference or only the absolute value of energy?
so these are absolute values of energy.
Okay.
These are absolute values of energy. Okay. So this tells me that at J equal to J max, just a minute, I have to take this. Hello, Lokesh, I'll call you back. I'm in a meeting. So J equal to J max is the energy level or is the quantum number for which the maximum population will happen. Now, how does this look as a, how does this look as a function of J? So this is how it looks. So what I'm plotting right now is the relative population of energy level Ej as a function of G. And as you can see that for a given temperature, this J max is not J equal to 0, but some value J equal to 4 for B equal to 5 centimeter inverse. And as I increase B, this J max is lower.
Sir, Ritu has said that in the energy population formula for Nj by N0, where Eg minus E0 should be there instead of Ej only.
Yeah, but E0 is 0.
Okay.
At J equal to 0, energy is 0.
Okay. Thank you, sir.
Yeah. Okay. So this is how the population distribution will be across the different J values. Okay. Now this brings to the next aspect of rotational spectrum, which is what happens if I have isotopes. Now, as you can see, the rotational constant B is proportional to 1 over I. And I, which is moment of inertia, is proportional to reduced mass. So if I have a heavier isotope, my reduced mass will be heavier. If I have a heavier reduced mass, my moment of inertia will be larger. If I have a larger moment of inertia, my rotational constant will be smaller. If I have a smaller moment of, if I have a smaller rotational constant, you can see from J max expression, the J max will be larger. That means the heavier isotopes will have higher rotational levels being more populated. Is this clear?
Yes, sir. It
Good,
is.
good. And in another word, another way you can see this is that as I'm going to heavier mass, my energy gap or the rotational constant reduces. So the energy gap between rotational level reduces. And that's why for a given temperature with a given energy, I can access higher and higher rotational levels. So that's how you can look at it. Okay. So in other words, with heavier isotope, the rotational energy levels come closer, and hence the population in higher J can increase at the same temperature. Okay. So far we have seen the diatomic molecule as a rigid rotator. But is diatomic molecule really a rigid rotator? The answer is no. And why it is not a rigid rotator? The simple reason is that the molecule is also vibrating. That means as a function of time, the molecule has a different bond length. So we have to look at the average bond length. But what matters for our moment of inertia is not average bond length. What matters is the average 1 over r square. And 1 over r square is not same as average. Average of 1 over r square is not same as 1 over r average square. And this you can verify yourself. And because it is not, that means my equilibrium distance will keep changing if I'm going to have different vibrational excitation. And we will come to this point in tomorrow's lecture where we will bring in the vibrations. We will club vibrations and rotations, and we will see how these rotations affect vibrations and vibrations affect rotation. Is this clear? Okay. So
Yes, sir.
now it's already 8 o'clock. So if anybody, and I know it has been very tough day or long
One
day.
small request is there to explain the last point again.
Okay. So the last point is following. In so far, we have treated the diatomic molecule as a rigid rotator. What do you mean by rigid rotator? The bond length is fixed. Okay. However, our diatomic molecule is not fixed. It is not frozen. It is vibrating. Now, if it is vibrating, that means at different points in time, the bond length has different, or the distance between two molecules or two nuclei is different. So, is that the case that on an average, this number is going to be a fixed number? No, it depends. It is going to depend on different vibrational level, and that is why our rotator is not going to be a rigid rotator. It is going to be a non-rigid rotator. The simple explanation for that is what matters for rotational constant is moment of inertia, and that depends on 1 over r square. But 1 over r average square is not same as average of 1 over r square. And this you can prove. Okay? This is a simple example of spring.
Yeah, thank you, sir.
Yeah.
One small announcement for the candidates. Please note that I have put the attendance link both on the YouTube platform as well as on the chat box of Zoom. So please fill in time.
So, Dr. Vaibhav, it was a very nice session, and definitely. So, I think of the time when I was taught molecular, was never presented in such a simple manner, and this exactly is the manner that it should be presented in. So, I really enjoyed it personally, the whole of the talk, and the crystal clear way by which it progressed from step to step, making them realize these very small things. Just today morning with undergraduate students, I had difficulty making them understand that a gamma ray photon and an X-ray photon energies and wavelength and frequencies, how they are different and how you can do just the back of the envelope calculations without going into great details and still understanding. So some of those students are here in your talk also, and I'm sure they would have realized the importance of this. So thank you once again. And I'm sure that the students are also joining me. Yes, the chat box is full with thank yous for you. Your
I
note
have
was also very good.
a small exercise for all the kids,
Yeah,
at least those kids who have access to microwave oven.
yeah.
I will request that you remove the rotating disc from the microwave oven, take a saucer, and take a cheese slice, keep it in the saucer, and keep it in the microwave oven for a minute. Why I'm asking you to remove the rotating disc, because I don't want that microwave oven to rotate your cheese slice. Just it should remain stationary at one place in one orientation, and irradiate that with your microwave and see what is the wavelength of microwave that you get.
Good, good, good homework. Practical, good homework.
Yeah.
That's a nice one.
The microwaves are actually not micron waves, it's actually centimeter waves.
So I thank you again, Weber, for taking out time. I'm really grateful. And I'm sure all these students who are going to view you also later on YouTube will join me for your lecture. So thank you again. We'll see each other tomorrow again.
At
Yeah.
5 o'clock, right?
Yeah, 5 o'clock. Yes. 5 o'clock.
So tomorrow
So
I mean, with this speed, I don't know whether I will be able to finish whatever I have.
no, you were a bit slow. They have finished all the courses. So this is the last week. So they're not on the level, they're not on the ground zero level, and you can go a little bit fast. I think they will be able to take up with that.
Okay, because I
So
thought it's the last session and they must be very tired. So I thought I will go a little slow so that they are with me. So tomorrow
yeah,
I will go a little faster so that I can cover as much as I want to. Let's
yeah,
see.
sure. We look forward to it.
Yeah.
Thank you so much. Thank you so much once again.
Thanks a lot, sir. And indeed, it is a very interactive session. And even on YouTube, we got so many answers and comments as students are interacting with you through
So
questions.
students are asking for books, Vaibhav. Tell them some books. They are never satisfied without asking every lecturer about the books. So you please tell them some books that you like.
So actually, that the standard book for rotations and vibrations are Manuel. That's the standard book that one in principle can use. Bransden and Joachim. That's another very good book. I personally like a book called Molecular Quantum Mechanics by Atkins, and that gives a very nice. It has very good pictures and also gives a very nice description of diatomic molecules. And if you want to dive deep into it, then Hertzberg, of course. You can go and read.
Yes, I was going to add that. If you want to dive deep into it, then Hertzberg is the answer. But then it really keeps you completely engrossed.
Yeah.
And that's what we used in our masters. So great. I hope the students have realized that every speaker is telling them the same set of books and that they are not changing from speaker to speaker. So we had for atomic physics Professor Anirban Kundu from University of Calcutta, and also Professor Hashmi from University of Delhi. So they too mentioned the same set of books to them. So thank you once again. And Dr. Varsha, I request you to display the slide for tomorrow, share it, and then stop the live recording after sharing it.
Just a second, ma'am.
So we will have at 6 o'clock we'll have electromagnetic theory, and at 5 o'clock we'll have Dr. Weber with us once again for molecular physics.
Yeah.
So, Dr. Varsha, then now you can stop the live YouTube recording. Students, take note of the feedback link, because we will be closing it after 10 minutes. Yeah. So, thank you, thank you, Varsha.
Yeah. Thank you so much, ma'am. Thank you, sir.
Yes,
Good night.
thank you.
Should I stay back for 5-10 minutes? If people want to ask questions, they can feel free to ask me.
If you want to ask questions, then write immediately on the chat box, or we shall end the meeting. Please respond. They're still seeping in with whatever knowledge you have granted them today. No more questions, it looks like. What about on YouTube?
No questions, ma'am.
No, no further questions. Okay.
Thank you. Lot of thank
Okay.
yous are there. Yeah.
There are lots of thank yous.
Yeah.
Okay, Varsha, you can stop the meeting then.
Thank you, ma'am. Thank you, sir. Have
Good
a
night, Vaibhav. Good night, everybody. Stay safe, stay healthy.